got here neodymium disc magnets, very strong magnets. I've put some 12 of them, 12 discs together to make a very powerful magnet. We know that magnet attracts iron. These are all iron things. Two screws and this crocodile clip, all are made up of iron. Magnet also attracts nickel and cobalt. These materials which are attracted to magnet are called ferromagnetic materials. And I have here aluminum cylinder. Aluminum is not ferromagnetic material. There is no attraction between the magnet and aluminum. But watch this. No attraction. But when I start moving the magnet, the aluminum cylinder follows. Amazing. Watch that. No attraction. But I can make the aluminum cylinder move by moving the magnet and also make it stop. Watch this again. We can almost control its motion by the magnet. The magnet is not touching the cylinder. What's happening here? There is no attraction, but still we can control the motion of this aluminum cylinder using the magnet without touching it. To understand what's happening here, we'll have to understand two phenomena related to electricity and magnetism. The fact is, electricity and magnetism are related, interlinked. One phenomena is electric current produces magnetic field. This is a natural fact. And changing magnetic field produces current in the conductor present in that magnetic field. Two opposite phenomena, two opposite natural facts related to electricity and magnetism. With this setup, we are going to have a look at the first effect involving electricity and magnetism. This is a magnetic compass, and what you see inside, the moving part, that needle, is actually a magnet, and when not disturbed, it always points in north-south direction, aligning itself in Earth's magnetic field. This magnetic compass will be disturbed from its natural alignment in north-south direction by presence of another magnetic field. Look at that. I just brought a powerful magnet near it and it got disturbed from its natural position, and it will be also disturbed by another magnetic material like this. This is an iron screw. Iron is ferromagnetic material, and it will disturb or move the magnetic needle from its natural position. And here in this experiment, we are going to use this property of the magnetic needle to detect a magnetic field around it. This is a copper wire. Copper is not a ferromagnetic material, and it has no effect on that magnetic needle. And what we will do is, we'll keep this wire parallel to the magnetic needle and pass current through it and watch its effect on the magnetic needle. I've already connected one end of the wire to the battery. Let me connect the other end and watch what effect it has on the magnetic needle. Look at that. The magnetic needle deflects from its natural north-south alignment, clearly indicating a magnetic field is being produced whenever there is current in the wire. This experiment was first performed in 1821 by Hans Christian Ørsted, and he established that electric current produces magnetic field. Fact number one involving electricity and magnetism. Electric current produces magnetic field. I will invert this wire, place it like this, and pass current again, and watch the deflection. This time the deflection is in opposite direction. Look at that. So direction of magnetic field produced by this wire depends on the direction of the current in the wire. So this is the first fact involving electricity and magnetism. The electric current in this wire produces a magnetic field around the wire, all along its length. Electric current in the wire is flow of electrons, charged particles. Electrons are negatively charged particles. So we can generalize the statement, moving charge produces magnetic field. And with this setup, we are going to have a look at the second effect involving electricity and magnetism. This is a coil of 300 tons of insulated copper wire. This type of wire is used in winding of motors and transformers. 4 powerful magnets put together to make even more powerful magnet. Current indicating instrument called galvanometer. This does not read current in amperes. It just indicates the presence of current. That pointer, which is currently at 0 reading in the center, will deflect whenever there is current in that coil is connected to this galvanometer. We're going to use this to detect the current and also to detect the direction of the current. Right now, the magnet is not moving with respect to the coil, but watch what happens when I start moving the magnet with respect to the coil. Left to right, any which way, any direction, up, down, sideways. As long as magnet is moving, the galvanometer is showing there is current in the coil. When I stop moving the magnet, there is no current in the coil. This effect was first studied in 1831 by Michael Faraday, 10 years after Hans Christian Oersted's experiment, and he discovered the opposite phenomena. Changing magnetic field induces current in the conductor placed in that magnetic field. Amazing. So the first effect is electric current produces magnetic field, and the second effect is changing magnetic field produces current. Michael Faraday called this effect electromagnetic induction. He studied this in detail and formulated two laws of electromagnetic induction. Faraday's first law is very simple. It just states whenever magnetic field associated with a conductor changes, current is induced in that conductor, like this. Faraday's second law is also easy to understand. Watch the speed of motion of the magnet and the deflection of the needle in the galvanometer. When I move this magnet slowly, you see some deflection. When I move the magnet fast, watch the deflection, it's huge. If I move the magnet slow, lesser deflection. If I move it fast, more deflection. So his second law simply states that amount of current that is induced in the conductor is directly proportional to rate of change of magnetic field. Slower the rate of change, lesser the current. Higher the rate of change, more is the current. Faraday's second law. There is one more effect involving electromagnetic induction, and we know it as Lenz's law. When the magnet moves, it induces current in the coil, and that current in the coil will produce its own magnetic field. And the direction of that magnetic field will oppose the motion of this magnet. That is Lenz's law. What Lenz's law states is the direction of induced current is such that it will produce a magnetic field that will oppose the change that is producing it. And what Lenz's law means in this case is it's the motion of the magnet that is producing the current in the coil. And as I lift the magnet, the deflection of the needle in the galvanometer is on left, and when I put it back, it's on the right. And clearly we can see the direction of the induced magnetic field of the coil changes with the direction of the motion of the magnet. And that magnetic field of the coil produced by the induced current will oppose the motion of the magnet. I can actually feel the pull of the coil as I lift the magnet up. I can feel the coil pulling it down, and when I try to keep this magnet down into the coil, I can feel the push of the magnetic field of that coil. Lenz's law. Induced current will oppose the change that is producing it. So now we know two interlinked phenomena. One, electric current produces magnetic field, and second, electromagnetic induction. That is, changing magnetic field induces electric current, and an effect related to electromagnetic induction called Lenz's law, which states that induced currents are such, their direction is such that they will oppose the change that is producing the induced current. We'll understand all these three things, and we'll also try to understand what's happening here. Aluminum, magnet, no attraction, but aluminum cylinder rolls along with the magnet. And also I can stop the rolling cylinder just by placing magnet over it. Watch that, I'm not touching, the magnet is not touching the cylinder. So what's happening here is, this is the aluminum cylinder, there are free electrons inside. And when I move the magnet over this, we are inducing the current in the aluminum piece. And these induced currents are called eddy currents. It's something like a whirlpool of free electrons inside. The currents remain confined in this aluminum piece. Eddy currents. They are small, tiny whirlpools of electrons. I still cannot visualize how they actually look, how the current looks. I cannot visualize it, but yes, definitely eddy currents are present in this when the magnetic field related or associated with this changes. Those eddy currents produce their own magnetic field trying to oppose this magnetic field that is changing. And how does it do that? Best thing it does is tag along with the magnets, go along with the magnets, opposing the change of magnetic field and trying to minimize the production of eddy currents. Lenz's law in action. And when this aluminum cylinder is set in motion, I can stop it just by placing magnet over it. So it stops moving to reduce the change in magnetic field and eddy currents, and it moves along to do the same thing, to resist the change in magnetic field and minimize the production of eddy currents. Amazing. Let us have a look at the variant of this experiment. This is a variant of the experiment we just saw. What I'll do is I'll just place this aluminum cylinder on this wooden plank and let it roll and try to stop it with the magnet without magnet touching the aluminum cylinder. Let's do that. There you go. Stop, 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 stop. Repeat. Stop, stop, stop. So eddy currents stop that aluminum cylinder from rolling. Let me try to roll this uphill without touching. Yes, we can do that too. Watch that. The magnet is not touching the aluminum, but still we can roll this cylinder up. Stop, stop, stop. Amazing. Electromagnetic brakes work on this. Eddy current brakes work on this principle. So those are eddy currents in action. Let us have a look at more such effects, fun effects of eddy currents. Here is one more effect of eddy currents. This is a wooden strip, a copper strip, and the same neodymium disc magnets. Wood is certainly not a magnetic material, we know. There is no attraction between wood and magnet. Neither is copper. Copper is not a ferromagnetic material, just like aluminum, and there is no attraction between magnet and the copper strip. Let us watch this fun effect. What I'm going to do is I'm going to just place this wooden strip at an angle like this, forming an inclined plane. Place the magnets on top of it and watch what happens. Just slides down. Watch that again. Let me balance it properly. Quickly the magnets roll down. Now let us repeat this with copper strip. So here I'm keeping the copper strip inclined and placing these magnets on top of it. Watch that. It's reluctant to slide down. It was sliding down so quick on the wooden strip here, but it's reluctant to slide down. Watch that. Somehow doesn't want to slide down. What's happening here is the same thing, electromagnetic induction. As this magnet is trying to slide down the copper strip, it's inducing eddy currents in the copper strip here. Those eddy currents are producing magnetic field, and the direction of that magnetic field is such that it will oppose the sliding of this. Lenz's law. The induced currents will be such that they will oppose the change that is producing it. The change here is sliding of the magnet, and hence it will oppose the sliding magnet. Amazing. We'll have a look at few more effects of eddy currents, fun effects of eddy currents. Here is one more fun effect of eddy currents. This is the pendulum. The bob is the magnet, powerful magnets. Let me set this in oscillations. Nicely and freely this is oscillating. Let me slide this copper strip under it and it stops. Repeat. We'll put this in oscillations and just slide this and look, it stops. It applies the brakes on oscillating magnets. Same story here, electromagnetic induction, Lenz's law. The oscillating magnets induce eddy currents in the copper strip. Eddy currents in turn produce a magnetic field whose direction is opposing the motion that is producing it, the motion of the magnets, the oscillations of the magnet. Amazing. Once again. And now watch this. Keeping the copper strip under the magnet pendulum, and we'll try to oscillate this. Watch again. It just refuses to oscillate. It just refuses to move. Watch that. Eddy currents in action again. There it goes. And look at this. The magnet wants to move along with the copper strip. Here is one more interesting effect of eddy currents. Powerful disc magnets, PVC pipe, aluminum pipe, and an aluminum cylinder that I've created using aluminum foil, the wrapper foil that is used to wrap food items. These are recycled aluminum foils, and some final turns are of fresh aluminum foil to give a good finish. And I've wrapped it in a plastic sheet just to protect. Let us watch this fun effect. What I'm going to do is I'm just going to drop this magnet through the PVC pipe and watch. It instantly drops down. It falls down at the normal acceleration due to gravity at this place. Let us have a look once again. It quickly passes through the pipe and drops down. Let us watch the same thing, and let us watch what happens when I do the same thing with aluminum pipe. It takes much longer. It doesn't fall down with normal acceleration due to gravity. There is some kind of resistance to it and it slows down. Watch that. Once again. Much slower. Much slower. Let us watch its drop through this aluminum cylinder. There's a PVC pipe at the center. Aluminum foil is wrapped around it. I'm going to drop this through aluminum cylinder here. Takes much longer. What's happening here? Same thing again. Electromagnetic induction and Lenz's law. As the magnet falls down, the magnetic field associated with this aluminum pipe goes on changing. Eddy currents are induced in this aluminum pipe, and the magnetic field of that eddy currents resists the change that is producing it. What is the change? The falling magnet. So the eddy currents in this will produce a magnetic field that will oppose the fall of the magnet and slow it down. Amazing effect. Super. So that was fun with eddy currents. There are many applications of eddy currents. One is electromagnetic brakes. You just saw how I could stop the rolling aluminum cylinder just by placing magnet over it. You also saw the oscillating pendulum stop when a copper strip is placed under it. This is the principle of electromagnetic brake or eddy current brakes. Eddy currents are also utilized in one of the very common equipments in our kitchens now, the induction cooker. There will be a separate video on how induction cooker works. And there is also induction furnace, which is used to melt the metal pieces, iron pieces. Amazing effects. I hope you enjoyed this video. If you like such videos, if you like to know the secrets of nature that are revealed by physics, keep watching the videos on my channel. Like them, share them, and do not forget to subscribe to my channel. Thank you.